Vsauce, Cooper here. Numbers. They're crazy, right? Some have funny little round bits, others are totally pretentious. Take this one for example. Get it? Pretentious? Of course, that's only a joke. Numbers don't have personalities. They can't be loving, spiteful, or irrational. But there is such a thing as an irrational number. But what does that even mean? Is there a number out there that can rationalize thought? And does it do it poorly? Well, no. And it may be more accurate to call this sort of number an incommensurable ratio. This means that the number cannot be written as the ratio of two integers. For example, the square root of 2 can't be written this way and is therefore incommensurable and irrational. Simple, right? Well, it wasn't always that simple.
Because math used to be a whole lot cultier. I'm Mike. Welcome to Crash Course. You've probably heard of this guy, Pythagoras, famous for his triangle math that you had to hear about in middle school and continue hearing about until, well, now. Turns out you don't know the half of it. Dude had a freaking cult. The guy was so good at math, he had a cult. So here's Pythagoras, and he was good at math, like really good at math. And Pythagoras has this idea that every number should be able to be broken up into basic parts, and with that, you should be able to write every number as a ratio of integers. His followers ate this up because, well, they were a cult and all. But all was well, and everyone was happy with this and their math-worshipping lives, until one unfortunately brilliant guy came along. No one is absolutely sure who he was, but many say that Hippasus of Metapontum, member of the Pythagoreans, was the unlucky fellow. That's kind of a mouthful though, so we'll just call him Hippie. So, as the story goes, Hippie was thinking about triangles, as you would if you were in a math cult, when he discovered a property of certain triangles that would dismantle a core philosophy of Pythagoreanism. Yep, that's really what they call themselves. So Hippie, foolishly thinking that his breakthrough discovery was important or something, approached Pythagoras and said, "Hey, I think I found a number that you can't write as a ratio of integers." A concept that would later be known as irrational numbers, to which the ever-respectful and generally calm guy Pythagoras responded by throwing him into a lake and letting him drown. And so, in the end, irrationality was Hippie's downfall.
So what exactly did Hippie say to deserve a math-related mafia-style death? We're here with Dr. Pythagoras to talk about the irrational numbers.
That we are. Let's get right to the math, I suppose. It's actually a nifty little proof, the whole irrational numbers and whatnot. So it actually all starts with this triangle. Here, get a good look at this triangle. It's a good one. It's a 1, 1, and we know 1 squared plus 1 squared is 2, so this is root 2. And of course, we do know that root 2 is irrational.
So what's the big deal? I mean, they look pretty irrational to me.
Yeah, I suppose they don't look that different as root 2. Well, the actual exact definition of irrational number, incommensurable ratio, is that we can't have, say for some number x, we can't write it as a over b, where a and b are both integers. And so for root 2, we can't actually do that. And you know, it's not just that it goes on forever. I mean, there are other numbers like 0.111, you know, so on. That is tempting to call irrational because it just goes on and on and on forever, which is kind of irrational. But it actually can be written like this because it is just 1 over 9, and we just need to make sure that those are both integers, and you know, we can check it. Is 1 an integer? It is. And 9 is 2, so I think we're good. And this is actually not an irrational number. You need some long infinite series that does not repeat infinitely onward.
Something like pi should be an irrational number then?
Pi is a famous example of non-recurrent infinite number. So we get 3.1415926 3, 5, 8, so on. And of course, there is no pattern to it. It just goes on and on and on forever. I mean, it's non-recurrent at least. And so we know that that one is irrational too. It's probably the most famous irrational number. It's usually what people think of. But that is not how we could prove back then. I mean, we use a squared plus b squared equals c squared. You know, that is Pythagoras' theorem, so you'd think he would use that. It's his namesake. It's his most famous thing by far. But in reality, he never actually wrote it like this, or anything like this, in fact, because back 6000 BC, when Pythagoras was actually making any of these proofs, algebra was yet to be invented. In fact, it was invented much, much later. So it's actually sort of ironic that he's given a squared plus b squared equals c squared, because he had never seen it. It actually would be as unusual to him as math cults are to us.
So you are now invited to the math cult meetings? I mean, they are a blast.
Shh, don't blow our cover. No, but so they had to prove it some other way. They couldn't actually just use this nice little definition and all of this, of course. It's all fairly new, relatively, I suppose. And so they did it as such. You take your triangle, and you take the literal squares of each of them, as they did back then. That's why they're called squares, is you draw a little square off of each of them. And we say this one is a squared, this one is b squared, and this one is c squared, to be helpful for us. And so you need to use that to prove that there's an irrational number. And actually, Pythagoras defined his triangles, these sorts of triangles at least, as being in simplest form if there are no factors remaining between the sides. And he said they would all be integers, and that if there were a factor between one of the legs, you would just divide it out, and then you get your simplest form of your triangle, and that you could reason with all of them, and all the rest of them that are multiples of it are just multiples of it, and you can treat them the same way. So if we say this is in simplest form, they're 1, 1, root 2, then we can say, in fact, actually, that these two areas are the same, because they're squared, they're the same leg of the triangle, or the same length of the leg, and so their squares must be the same. Which means that we can actually divide c squared in half and say that each of these is equal to 1/2 of c squared. I mean, it makes sense. So then we can actually say that because this c squared is an even number, we know it is because it can be divided in 2, because it's in simplest form, we actually know that c is even too. And if we know c is even, then we know that its square is actually divisible by 4. 2c squared is 4c squared. So we can take it and separate into fourths instead. Now, because each of these is taking a half, we actually know that each of those halves is divisible by 2 too. So if we take that and we know that each of these squares is divisible by 2, then we actually know, by the same reasoning we used here, that each of these legs is also divisible by 2, which means that these can be divided by 4, and also that these legs are even, and this leg is even. So if they're all even, then what does that say? It says that it is not in simplest form. Each of these can be divided by 2. So that has proven wrong, that we define this to be in simplest form, and yet it is not in simplest form. You can't actually divide out all the factors.
So what happens if you just divide them by 2?
Oh, well, yeah, since they're all divisible by 2, you'd figure you just divide them by 2, and then you have simplest form, right? Yeah, I'm sure Pythagoras did something similar, and just a bit of a dick. So if we divide them by 2, then we actually get, so if we have our AAC triangle, our isosceles triangle, then we divide them all by 2, we get A over 2, A over 2, C over 4, ostensibly. So then we actually don't get rid of any problem, because these are still just, still an AAC triangle, it's still an isosceles triangle. So we can actually do the same principle. We say this one can be divided by 2, because each of these is equal. We divide this by 2, therefore this is even, therefore this is divided by fourths, therefore each of these is even, therefore each of these is even, and therefore is incommensurable. So you can do it infinitely onward, And because of that, you can never resolve this simplest form to an actual simplest form. And because there is no simplest form, there must be some number that does not satisfy commensurability. And by that definition, we have an irrational number. So there you go. Irrational numbers, they exist. Proved it here.